So good afternoon, everybody. Welcome to our 44th CCSS lunch when we're back online. Very happy to welcome Professor Lachman from Santa Fe. Just to introduce the session, we'll be on for about 45 minutes lecture from Michael, and then we'll pass the floor to you for the Q&A. So Deb will chair the Q&A. If you have questions throughout, you're welcome to post them in the chat, or he'll open the floor and you can put up your hand at the end and then ask your question verbally. So I'll pass the floor to Deb, who will introduce Michael, and then we can begin the session. Thanks very much. Enjoy the evening.
Thanks, Robert. So it is our great pleasure to have Professor Michael Lachmann to our complex systems talk. This is the great advantage of having him sitting in his own office. That's what it looks like, and still be virtually present in Holland. So I understand that he's been working in a large group which is centered around in Texas, Austin, on COVID-19 epidemiology. I'm really interested in that one, especially from my own perspective as well. And he is an evolutionary biologist, and he's so he got his bachelor's from Tel Aviv University, and then he did a PhD at Stanford, and afterwards he moved on to Santa Fe. And in between, and I'm not entirely sure if he's still associated with the Max Planck Institute for Mathematics and Life Sciences. Are you? No. So, well, in any case, now he is a full professor at Santa Fe Institute, and so he's going to tell us about his work on COVID-19 epidemiology and the origin of life. So, Michael, if I can address you directly by your name, the floor is yours.
Thank you. Let me share my screen. Okay, so I'm very excited. Thank you very much for inviting me. I'm very excited to give this talk. This talk will have like two parts, which in a way reflect my life in the last year and a half, because I tried to do both of these things. As Deb mentioned, I'm a professor at the Santa Fe Institute, and I worked on things like evolution of multicellularity and also signaling and the relation between information and evolution. And I also participated in Leipzig in the Neanderthal Genome Project. And so if any of you have interest in these things, I would be very happy to talk about that too. So over the last, over the last year and a half, since March 2020, I joined the COVID-19 Modeling Consortium at UT Austin. Ooh, why does it switch on its own? And it has a large, as you see here, it has a large group of people who come from many different areas. So just like I am an evolutionary biologist and I've never worked in epidemiology, many of the people that you see here just volunteered to help in the modeling effort. So Lorenzo is a mathematician, there's people from all over, and Lauren is the one that organized the whole thing. And Spencer Fox worked a lot with us. He was kind of the vice chair. So I'll start by telling you just a hint of what we were doing in modeling COVID-19. So COVID spreads among people. And here you see people walking around, possibly infecting each other or not. Modeling exactly what happens in a population is impossible. So whenever you model the spread of COVID in a population, you have to do some kind of simplifications. And I want to show you three types of models that we did in the consortium of predicting, understanding, and explaining. And actually, my view of what a model is changed over this year and a half. So I used to think that there's two types of model: predict and understand. Predict is when you basically throw everything in the sink-in. So you try to make the model as exact as possible. If you say want to model a forest fire or something like this, and understand, you make the model as simple as possible, but not simpler. So you try to distill it down to just to show that just one thing is important. But actually, over this year and a half, I got to see that this distinction isn't very precise, and there is a mixture in predicting. There is a mixture of understanding and vice versa. So let's look at the model that we use for predicting. So in order to model COVID, as I said, we can't really model every single individual and how they interact with everybody. So one direction that you can go is a network model, where you still model every individual, but you assume a certain network on which they interact, and then you see how the disease spreads. This is actually a model that we also used. It is a bit heavier. An alternative way is what's called compartmental models, which is what I show here. So in a compartmental model, you assume that the population is well mixed, so everybody can interact with everybody, maybe with interaction metrics. But then you have compartments in which there are people, and they move between the compartments. So everybody starts up in S. So this is, I'm sure you heard about SEIR model. So this is basically a big SEIR model. So people start up in S, and then if they get infected, they move to exposed. And then now they have a disease. So the disease, now they move according to the disease progression. Maybe they become symptomatic, and then they might go to the hospital, and then maybe they recover, and so on. So, and then all the people that are in this part can infect others. So this is a compartmental model, which is in a way it's an approximation to a set of differential equations. And in our compartmental model that we use for modeling, we have these 9 compartments, but then we have each of these is divided up into 10 other parts, so 5 age groups and 2 risk groups. So in a way, it is a compartmental model with 90 compartments. And you can see that as you add more and more states that an individual can be, for example, now we have to add vaccinated, maybe vaccinated with 1 dose, 2 doses, and then you can also have infected with the Delta variant or Omicron variant. The number of compartments can really explode as you add possible states that an individual can be. And then the advantage of the compartmental model that it is that it's easy to have in a computer kind of starts to decrease versus a model where you model every single individual. But for now, this is what we use. And then we also use mobility data that we got from a company called SafeGraph. And the mobility data allows us to adjust how much infections can go into the population. Oh, how does it go? Can people ask me questions during the talk, or is it only after?
We leave the last 15 minutes to questions.
Okay.
Yeah, unless you have a preference.
Yeah, I mean, if there are questions where something is unclear, it would be great.
Yeah.
People can.
Thanks.
Okay. I see there's a slide missing. Okay, so here, so we want to predict, right? This is what hospitalization admissions in Austin look like. Each dot is a day. And you want to predict forward. Of course, how could you predict? You could just say, well, it went like this, and let's continue it linearly, so it would go a bit like that, right? That would be one model where you just continue it linearly. Or maybe you fit a spline or something like this. Or you can fit an exponential growth model. So as opposed to these simple models that don't really look at what happens, we fit, as I showed you, this compartmental model, which then gives us the light gray lines are possible futures, and the blue line is kind of the median of all the predictions. And I don't actually think that such a complicated model as I showed you will give much better predictions than than a linear fit or a spline fit or something like this. I don't think that is its advantage. The advantage really comes from the fact that because we have compartments, we can we have an interpretation of what's going on inside. So we can, for example, here we have a graph that says how many people were exposed to COVID over time. Or we can look at this graph, how many are recovered over time. All these we couldn't get out of a simple linear fit. And because we have then this kind of internal interpretation of what the model thinks happened, we can then use this to say, I mean, one thing is we talked with the city officials where we can tell them currently out of, you know, every person in Austin, 1 over 1,000 is infectious or something like this. So we can give it such interpretations. So I think the advantage of a more detailed model comes from that you can interpret what's going on inside. And that's why I said that there's a bit of a mixture between the prediction part and understanding part. And another thing that we did, which actually causes the model not to fit very well, we also tried to intervene. So we were talking with the city officials, and we used this model and a very similar model in order to say, currently, the way things grow, the hospitals will run out of capacity in 3 weeks or in a month or in 1 week. And then the city could adjust, first of all, these levels like green, blue, yellow, orange ahead of time, because they could see if we stay in green for another 3 weeks, then we will hit in 4 weeks, we'll hit red or something like this. So they could plan how to adjust the levels that the city is in. And also, they could plan ahead and say, since it seems like no matter what we do, we will go 200 people over capacity, we should set up hospitals to treat people outside the hospitals. Okay, another type of model that we did is understanding. And here, so this is oh, I didn't put the link in, the citation. So this comes from a work by Dan Lachman and Michael Lachmann and others, where they showed that if people would test periodically, even with a test that is not so good, so what's called with a rapid antigen test or another other rapid test, if they would test every day or every 2 days or every 3 days, we could actually bring the pandemic down very quickly without lockdowns, without other interventions. In theory, though you should use also other interventions, what you see here is they kind of looked at what happens if people test weekly and only half of the people test, or if they 3/4 of the people participate and they test every 3 days and so on. Of course, this was still with the original strain. I don't think that the picture would be as rosy with Delta or Omicron, but testing periodically everybody would really help bring the pandemic down. So with this idea, we then wanted to help schools in Austin to try to decide how often should they test. Because the schools in Texas were provided with tests, and the question is how to use them. And in this case, one model that we did is again a compartmental model, but instead of the compartmental model that I showed before, we really want to model kind of what is the progression of how much viral load each individual has. So each of these lines is a different disease progression, where maybe this individual has a very rapid rise of viral load, whereas these individuals have kind of a very gradual rise. This type of modeling you need because you want to kind of be able to say how many people will test positive after 3 days. So this person would test positive after 2 days, whereas this person, the viral load goes very high only maybe after 5 days. So you want to have that in the model in order, right? I talked about how a model should be as simple as possible, but not simpler. In this particular model, the disease progression should be included. But otherwise, this model is much simpler than the 90 compartmental model that I showed you before. And so with this model, we can then build this kind of dashboard where the schools could adjust what the school size is, how often they test, and so on, and that would give them how much transmission is expected to be in schools, how much is imported, and so on. Finally, the last type of model is explaining. So this is when you kind of go to the public and you want to show them some part of what's happening with the disease. And in this case, we did something very simple. So at some point, I think this was July, in July 2020, schools wanted to open. And we just made a very simple point. We just asked, so at that point, we didn't know much about how well does COVID spreads in schools. We didn't know how well COVID spreads among kids and so on. But you can make a very simple statement without knowing anything about how COVID progresses. This is simply this. If currently the community prevalence is 1 in 1,000, so 1 in 1,000 are infected, and the school has 500 kids, what's the chance in a week that a kid will come into school infected? So that's a very, very simple, with simple assumptions, you can easily answer that question. And then the New York Times published this kind of site and article about it saying, like here in these regions, like 10 kids will come into school infected every week. So you have to, if you open schools, you have to plan for what do you do with 10 kids who are infected in school. Does it mean that you have to close the whole school immediately? Or does it mean that you will have to quarantine several classes and so on? So this just gives you kind of an interpretation. What will happen if you open schools? And it doesn't really need any epidemiological model. And it's very easy for the public to understand. So this is the end of the first part of my talk about what the main things that I did over the last year and a half and the types of models we did. Of course, we did many other models that I can't talk about. And I would be happy to answer questions about that. Okay, so now I want to switch to the second part of my talk. And that is actually my main interest in these days. So I said that I worked on, how much time do I have?
Another 30 minutes or so.
Great. Yeah. So as I said, I worked on the origin of multicellularity and the evolution of multicellularity. So not just how multicellularity emerges, but also how it evolves, how differentiation evolves, how tissues evolve, and so on. But actually, my main interest since before even being an undergrad was understanding the origin of life, and that was the reason that I came into biology. And I started working on it again, maybe 10 years ago or something like this. But sadly, over the last year and a half, I couldn't focus on it very much. So one story that I like to tell is in New Mexico, there are these caves called Carlsbad Caverns. And when you go into these caves, you see these amazing crystals. I mean, this is not the crystal from this cave, but there you see like really nice structures and crystals. And as a biologist, when you look at something like this, when I look at the moss, at something like this, right? As a biologist, I start thinking, also not as a biologist, like, what are these things for? Why is this part red? Why is this part green? And so on, right? You try to give a functional interpretation to everything, and then you say, oh, maybe this is green because it photosynthesizes, and these structures, maybe I don't know what they do. Maybe they collect water, or maybe they disperse pollen, and so on. So you give a functional interpretation to different parts. As a biologist, when I looked at this, I also wanted to start to give functional interpretations. I wanted to say, what are these things for? What is this thing for? And so on. But then it hit me that for things that grow in the cave, even though there is a process that generates them, but we can't really give a functional interpretation to this. I mean, of course, we know about this intuitively all the time, but in the cave, you know, like this could easily have been something, you know, like some kind of fungus, and then I could put a functional interpretation, but because it was just a crystal, I couldn't. So people have worked on the origin of life actually for, I think, longer than written history. I think people always wondered about how life emerged, and I think that when you kind of want to understand the origin of life is because you see that there's, in a way, like two different types of things in the world. There are things that seem to want something. There's like, you see an ant and it's crawling around and it looks like, I mean, in addition to having kind of a functional interpretation of what it looks like, there's also a functional interpretation of what it does. It looks like it wants to find food. It's trying to avoid you if you try to smush it and so on. Whereas then you have rocks that just lie there and don't do anything and don't seem to have any functional parts. And we want to understand where did the life things originate? And of course you can say there have been life things forever. So there's just two realms. One is live things and one is non-live things. Or you can try to give some kind of theory that says that God created it, or maybe actually the non-live things were created from the live things. There were like a live God and he laid down and generated the earth and so on. So there's various theories of how life emerged. And I think that many researchers, the direction that they're trying to go is trying to see what chemical reaction caused life to emerge, with the idea that there is some magic chemical reaction that if we just knew what it is and we put it together, then an evolutionary process would start, life would emerge. So some kind of recipe where we say, this is the ingredients we need, we put them together, and then stir just in the right way, and life will emerge. The reason, and then in that interpretation, part of the reason that there is life is just because for some reason in our universe, this particular chemical reaction gives rise to life. From my point of view, even if we found this magical recipe book that would give us the recipe of how to generate life, the answer that I would like to know will not have been answered. I would like to understand why life emerged, and for me, the answer that it is simply because this particular chemical reaction is possible, and if it wasn't possible, life wouldn't have emerged. That is a very unsatisfying answer. I want to find the principle of why life emerged. So we know that the way we see how evolution progresses is through these three ingredients interacting with each other. Of course, there's many other important ingredients, but it is replication, so things need to replicate. Then there's variation, so different individuals are different. And then there's selection. So you select among these different individuals, those who survive better go on and produce offspring into the next generation. And these three ingredients mixed in the right way together will give us then the diversity of life that we see now. And of course, we know that it's not as simple as this. And in the research about the origin of life, because these are the three ingredients, people have mainly focused on trying to get replication. So the idea is that if you have replication, everything else will follow. And these, so therefore, in these chemicals reactions that people try to build, they try to come up with things that replicate. Instead, in this talk, I will focus on another part of these three, and this is simply selection. So I will look at what what will we have if we just have selection in the system? So we don't, I'm not requiring, actually, can you see my mouse? Yes.
Yes, we can see it.
Yeah. I'm not requiring yet replication or variation. I'm just looking at selection. I will require pre-existing variation, so things will need to differ. And the claim is that selection among individuals or things exists everywhere in physics. So in prebiotic physics or in any dynamic system, you can say, I have these things, and then some of them don't survive, and I need to define what does it mean that they don't survive. The others survive, and this selection process is equivalent to the selection process that happens in biology. And this idea of that selection can act outside of biology is not new. So other people mentioned it here. Richard Dawkins mentioned it in The Selfish Gene. And George Price, who was an important theoretical biologist, and sadly didn't live long in his work in biology, also thought that we need to come up with a theory of selection. So let's look at just a few simple examples of what selection looks like. So one thing we can talk about is nuclear decay. We have maybe a nuclear accident, and atoms are ejected, some of them radioactive. As time goes on, atoms decay according to their half-life. And if we look at after the first 5 minutes of this, the atoms that were released, we will see a lot of very radioactive atoms. As time goes on, those atoms that are most radioactive will already have decayed. And then if we come back after a year or 10 years, we will see mainly atoms whose half-life can be measured in years, and those that whose half-life is a few seconds are already gone. So it's a simple case where we have selection. We define the entities as atoms, and survival here is not having decay. Another example that I like to play with is snowflakes. So we know that snowflakes grow in cloud. You have like some initial kernel where the snowflake starts growing, and depending on the temperature and the current and the local humidity inside the cloud where that snowflake currently is, the growth of that defines the growth of the snowflake. And as winds and gravity moves the snowflake in this column and changes the humidity and temperature of the snowflake, the growth of the snowflake changes. And now we could imagine to talk about survival of the snowflake as staying in this region where it can still grow, and non-survival is falling out of the cloud and precipitating. And here then we can imagine that there's a selection process, and maybe snowflakes that grow very dense initially will fall out of the cloud quickly, and those snowflakes that continue to grow and can maintain more buoyancy, those continue to grow and become bigger. So we see how then, if this is true, then the distribution of snowflakes that we see as snow precipitating on us will come out of these two processes. One is this physical growth process, and the second is this selection process, where if you're too dense, you fall out, and if you're not dense enough, you will continue to grow. So maybe here, if we look at snowflakes, maybe this snowflake started kind of not very dense, and that's why it grew quite large, and maybe this one is smaller because it was denser. So we see these two cases where the selection process will determine what we see. And I think there's many other examples that we can apply it to planets or asteroids orbiting the sun, and many other examples. And now I want to go a bit deeper into what can we do with this this selection if we apply it into physics. So there are two important equations in biology that we can apply in physics without using a replication. So these two equations apply directly without having replication in them. Of course, if we have replication, then we need to we cannot apply it directly because we assume that we still don't have any replication. One is Fisher's fundamental theorem, which says how quickly the fitness changes in a population over time. And the second is the price equation. This is the same price that I mentioned before. And this is the price equation, which in a way can be also seen as a generalization of Fisher's fundamental theorem. And the price equation says, how does the average property of something change in a population? For example, how does the average height of humans change over time? And it says that you can split it up into two parts. One is this part, and it says, well, how much does height contribute to survival? So do people that are higher survive better, or is there no correlation between, no covariance between your height and whether you survive? And the second part, you can simply say, each individual human, do they grow over time? So this is the average change in each individual human weighted by their chance to survive. And so this equation can then be taken over into physics, and we see that it simply, we split up the change in height into two parts. One is kind of a change that comes because of selection. So we are not looking at the same distribution of individuals anymore. Some of them dropped out. And the fact that they dropped out changes the average height or changes the average radioactivity and so on. And the second part is where the physics come in. So each individual changes over time. Maybe in atoms don't change their radioactivity over time on their own, but snowflakes do change their property over time on their own. So we split the change into the evolutionary part and the physics part. And now I'll give you a simple example to see what this gives us. So the example that I want to work with is a one-dimensional ideal gas. This is a very simple system that maybe many of you have worked with. And I want to show how we can apply selection even in this simple system. So when we talk about the one-dimensional ideal gas, we can talk about the phase space of each individual particle. And in this phase space, because it's a one-dimensional ideal gas, there is an x-coordinate, which is this one dimension. And then we have this dimension that we show here is the momentum of the particle. So this particle has a momentum of maybe 3, and therefore it changes its x-coordinate over time. And here I think I'm assuming that it wraps around. Now here we have two particles. This one has a lower momentum, this has a higher momentum. So you see that this one on top moves faster. And this is how the particles will move through their own phase space. And of course, the phase space of the whole gas is the n-dimensional, in this case, 2 n-dimensional phase space where we take the phase space of each particle and multiply them together. Then we can look at an ensemble of particles. So these particles all have different x-coordinates and different momenta. And now we can ask what happens to this ensemble over time. And whoops, sorry. I pressed the wrong button. Just a second. Okay, I hope it doesn't happen again. So here's the ensemble. And now we want to say, I say that I want to apply selection on it. So we have these particles. Wait, but what? Yeah, so we have these particles. And now I'm looking at the selection process where the particles move out of a certain region in space. So we have particles that are inside a one-dimensional bottle. So this is the bottle from 0 to -0.5. I open the bottle and let the particles escape in this direction, in the plus direction. So all these particles have positive momentum. You can also add the negative momentum, but it's simpler to illustrate without them. And now I'm looking at the selection process of staying inside the bottle. And what will happen is that the particles will kind of slowly move out, and you see, of course, the speed at which they move is linearly related to their momentum, since they all have the same mass. And you see that the fast particles of course move out of the bottle first. The slow particles, maybe those that don't move at all, stay inside the bottle. And so what happens is then that the particles inside that remain inside the bottle decrease in their momentum. I mean, they don't decrease. There was a selection process where those that are faster left. And because of this, the gas inside the bottle cools down. Of course, we all know about this process, that when you release pressure from a bottle, the temperature goes down. Now we can use the price equation to interpret what happens here. For example, we can talk about the change. So Z can be taken as the speed of a particle. And we can see how there's a covariance between the speed of the particle and whether it remains inside the bottle. In this case, this part of the equation is 0 because the particles, because it's an ideal gas, the particles don't change their speed over time. And now therefore we can say, like, we can describe the change in speed of the particles inside the bottle using the price equation. And we can also give it this interpretation, as I said. This is the evolutionary part, and this is the physics part. We can also look at various other properties, right? We don't just have to look at the speed of the particles. We can look at their kinetic energy, or how far they are from the edge, or maybe how far, like what's their color or something like this. Some things won't change and some things will change as a result of the selection process. So now, so you see here that it seems because the gas inside the bottle cooled down, it seems as if its entropy decreased, right? And of course, we know that the only reason it's possible is because the gas was initially inside the bottle, and as it was released, entropy of the whole system increased, because now we know less about where the particles are. And while this increase happened, a local decrease can happen of where now we know that the particles that are inside the bottle, we know their momentum better. And this is very similar to what happens in evolution, right? We know that over the evolutionary process, we are individuals that kind of countered the entropy, right? We eat in order to maintain our composure, our kind of low entropy state, and also over evolutionary time. Through the selection process, the complexity that makes me, or that makes individuals, was formed by this selection process that decreases the entropy of the individuals, and of course does it by consuming negative entropy from the sun or from other individuals. So now I want to kind of describe what happens to this a bit more in detail. In order to do this, I use the Kullback-Leibler divergence. So Colbert-Leibler divergence comes from information theory, and I like to see it as a better way to talk about mutual information than the actual mutual information is. So you can write mutual information as a sum of Colbert-Leibler divergences. The general interpretation of Colbert-Leibler divergence is, how much do I lose if I think U, but the truth is P? So maybe I go into what's it called? A casino, and I bet, assuming that the distribution is Q, but actually the distribution is P, how much more money will I lose? So that is the kind of interpretation. Or if I compress a file and I think that it's a picture, but actually it's sound, how much more space will it then take? This is in general the interpretation of Colbert-Leibler divergence, and you can also, as I said, you can use it with when you get signals. So if I get a signal S, how much, if before I got the signal I thought that things are P, but now that I get a signal, I have the condition, I can condition on that signal, and then how much would I have lost if I didn't have the signal? So that's another way you can use Colbert-Leibler divergence. But another interesting way you can use Colbert-Leibler divergence is to say, in physics, if the equilibrium distribution of a system is P equilibrium, and the current distribution, the current ensemble that I have is P, then how much free energy can I extract out of it? Or another way to say it is, how much free energy would I need to put into the equilibrium in order to go to P? And this is related to Landauer's limit, which kind of says, one interpretation is, how much free energy do I need to use in order to erase computer memory? So if I erase 1 bit of memory, I will have to put in, the amount of energy I have to put in is kT log 2. And so this free energy gives us this formula gives us a free energy interpretation of, if we have an ensemble and we know we measure how far it is from equilibrium, we know how much free energy it has. So now we can use it for this ideal gas, and I'm sorry that I play here a bit with moving between ensemble and particle. So I'm assuming, even though I show here where the different particles are, I'm assuming that I have an ensemble of this state. So, but it's kind of, here it is equivalent to look, whether you look at an ensemble of a single particle or an ensemble of many particles. So I will not go, I will talk as if this is really the ensemble. So we know that we start with this state where all the particles are inside the bottle. And now we can measure the free energy as how far this ensemble is from the equilibrium distribution, where they can be everywhere. This is the free energy available to the system. And then, as I showed you, as the particles move out of the bottle, you could interpret it as if some of the free energy was used up, because now the particles can be anywhere in this compartment. Whoops! I think I have the wrong slide show. And now we can divide. So we can also look at the free energy here in this state, and we can ask how far is this from this. And now we can divide it into 2 parts. One part, we can talk about the free energy that is in the momentum, and we can say we have a distribution of momenta here and a distribution of momenta here. How far is this from equilibrium? So this is the fact that the gas inside the bottle is cold and outside the bottle is warm. And this gives us a certain amount of free energy. And then we have the rest of the free energy, that is the rest of the distance between this ensemble and the equilibrium. And this is still some free energy that is left, right? Because there's still particles that are inside that could move out. We still didn't reach an equilibrium distribution. And this division of the free energy into these two parts now can be interpreted as the first part, where you have these difference in speed, that is the functional part. So the faster particles moved out of the bottle fast, the slow particles stayed in the bottle. Now, in a way, particles know that to stay inside the bottle, they need to be slow. So this is a functional, the selection process put functional information into our system. Whereas the rest is kind of just the rest of the free energy. So we see that the selection process, initially the particles, and we knew nothing about what should particles do in order to stay inside the bottle. Once selection happened, this information came into the system. So the free energy that was initially there, without this initial free energy, nothing could happen. Because we have this free energy, some of it became functional free energy. So it is simply a part of the free energy is now in the difference in momenta between inside and outside. And then there's the rest of the free energy. So we see that the selection process splits up, generates functional functional information, functional free energy out of the initial free energy that we have. And I think this is a general process that happens in every system where a selective process can generate function. So in addition to the decrease of entropy or increase of entropy that we have in every system, I think parallel to it, we also have this process that I point out here, where you have an increase in functional information in a system. Of course, this does not have to happen in every system. So in some systems, it will not increase. And as you see here, when we reach equilibrium, at some point, the functional information decreases because particles move back into the bottle. So, but there is, I think, a generalized generation of functional information in the system. How much time do I have now?
If you could wrap it up, it'd be helpful. So we're a bit over time, maybe a few minutes, 2, 3.
Oh yeah, okay. Okay, so I'll do it quickly. So with this interpretation, now I think that we can bring function back into physics. So the big thing that Darwin did is he brought us an explanation of how is function formed inside biology. Now we can say that we know how these butterflies became black, and so their color is functional, these moths. We can now bring it into physics, where initially kind of asking what's the function of the rings of Saturn seems to make no sense. But if we now talk about snowflakes, we can bring functional language in, and we can say, what's the function of the hole in the middle? So maybe this hole in the middle, the way the snowflake started growing, allowed the snowflake to stay in the cloud for longer. So it plays a functional part, just like the low speed of the particles that stayed inside the bottle allowed them to stay in the bottle, and that is a functional part. So we can bring functional language back into physics. And yeah, so that's the end of my talk. Thank you.
Well, thank you for an interesting talk. Now, there are, let me see if, how does this go again? I guess people should just raise their hands if they have questions, right? I don't see any hands so far.
Carolyn
I see now. Yeah, Kalovian, if I can pronounce your name well, go ahead.
Yes, hello, that was correct. Thank you. Thank you for the talk. It was quite interesting. I had questions on both parts of it, but I'll just ask one on the first part, the COVID-19 related one. And I was just wondering, as you were talking about the predictive model, I was just wondering how you evaluate the performance of those models, and then how specifically the one you were talking about in some of its application, how successful have you been in sort of practically applying that and using it for decision making?
Yeah, that's a good question. I have to admit that at the beginning of the pandemic, we couldn't really evaluate the model very well. I mean, everything was just so hectic. But over time, we can compare the performance of the model to what actually happened, right? And today we can go back in time and compare what the model predicted to what it did, and we can compare it to other models, and we can see that. I mean, if I go, I don't know if I can quickly go back. You see, this is what happened in Austin, and this is something that happened in many places, which I think is not fully explained. So you see these long stretches where nothing happens. It just stays. Doesn't go to zero and doesn't rise exponentially. It just stays at some intermediate level. These parts are very hard for an epidemiological model to explain. A model that actually works really well, or maybe not a model, a prediction, is simply saying what happened yesterday is what will happen tomorrow. So things will stay constant. And these models do really well during these times. And actually, these types of models are very hard to beat because our epidemiological model has actually a hard time to stay here. But they have a hard time explaining these peaks. And the peaks are actually the times that most interest you because you want to pre-plan what to do in the hospitals and so on. And so what we did is we evaluate the model versus various other models and see how they do, and also look at how well they do in times of the peaks. But as I said, because we interfered, right? So what happened in Austin is not independent of our models. When we predicted that things will go bad, the city tried to change the behavior of people, or like lockdown was I mean, it doesn't have to be that it was done because of our model, but in Austin, partly it was because of our model, but in general, like measures were put in place, like masking, staying in place, or opening up, and so on. So these things will interfere with how well our model performs. And part of the reason for modeling is in order for the model not to work well. We want the peak not to go to reach herd immunity here.
Yeah. Okay. Yeah. Thank you very much, Michael. Thanks for that.
Let's see. Any other questions? So in that case, I have one myself. This the use of Kullback-Leibler divergence actually shows that it essentially shows the effect of our undercounting or overcounting, depending on whether the distributions of different random variables are overlapping or not in a certain situation. So you have now given an example where you could show, using an inert system, so non-biological system, that they actually do capture the loss of information, and in order to show that, you have used the free energy. And so I always have a bit of a difficulty in, let's say, one step back. So you have used a procedure which is common to in these biological information systems, and you have used it into a physical system. But the other way around is not always clear. For example, how would you use free energy in a biological system? Is the question clear? I'm not sure if I'm making it clear. So it's one way. It's
yeah, no,
easier
I think it is clear. So, and it is actually a very, very good question. So you're asking, someone can say, look, like you said, where is it? Yeah, here, right?
Yeah.
This KT log 2 to get like 1 bit of information.
Yeah.
It's a very, very small amount of energy. So is this limit at all relevant in biology? You know, when I when I grow, you know, and there's like I make a decision in the growth that is 1 bit, or in evolution, right? There's a selection process where half the individuals die because they had the wrong color, right? The moths had the wrong color. Of course, the amount of energy that was put into the system, free energy that was put in the system when half the moths died, right, is much, much bigger than KT log 2, right? It seems that there's no relationship between the two, right? I mean, building a single moth requires a huge amount of free energy. And then this minuscule, who cares about this minuscule little part that was part of it? Right, this is your question.
Well, I was going one level deeper. Is it even possible to define free energy in these contexts? That is, it's a very equilibrium concept, and we know that biological systems are not necessarily in equilibrium. So how do you even define these things?
Yeah, I mean, I think this is a problem that is more inside physics, right? So, I mean, we know today that you can use kind of non-equilibrium statistical mechanics with where you look kind of, instead of looking at the equilibrium system, you can look along a path going forward, and you can ask, what's the relationship between the chance of different paths? And there's also this relationship where you compare paths going forward and backward. So there are ways to define free energy in non-equilibrium systems, right? And we know that I mean, we use free energy when we design cars or when we build computers. So we know that it's a concept that can be applied outside equilibrium. I mean, I think we have to do it carefully, and it is actually, you know, like when I do these calculations that I showed here, when I do them carefully, I have, these are the problems that I encounter. But it's not that, I don't agree that free energy can be applied only in equilibrium.
I was not saying that, but I was curious how you do it, because I myself struggle in using free energy concepts and free energy minimum giving us a solution in a system which has continuous energy input and output in a big chunks of energy input and output. So far from equilibrium systems, if you like.
Yeah, I mean, yeah, it still is a problem for me. So here, when I showed this state, so the system went from this state to this state, where now there's particles here. But it is, in a way, there is a problem here. Like, how do you define free energy here in this state? Because if you look at the ensemble, right, the volume of the ensemble did not change. It simply changed its place. But now you can define kind of the equivalent system where you would say, like, what's the free energy if we had particles that had this speed outside the box and particles that had this speed inside the box? What would be the free energy of that state of the system? So this is one way to solve, to define kind of what's the free energy in this state, where you say, like, I have cold gas here and hot gas here, and then how much free energy would this system have? But you're right, it is a problem of this that I have to solve when I do this calculation.
Are there any other questions from the audience? Well, in that case, let's thank Michael once more.
Thank you.
Let's see, where are the hands? Otherwise, we do it like this. Just a quick question: is it to Robert? Is it okay if I stay online for? I mean, if provided Michael has time for a couple of minutes. Otherwise, if I mean, if you close the session, if we all disappear, then this will not happen.
Yeah, exactly.
I mean, you feel free to stay on. That's not a problem.
Yeah. And also, if anyone has questions about this or other things, I would be happy to talk with anyone.
Super. Well,
just email me and then we can meet.
Yeah, I won't close the session. So if you would like to have,
I just want to have one-on-one discussions.
Super.
So
well, thanks very much, Professor Lachman.
Thank you.
Enjoy the rest of your day.
Thank you.
Thanks.